Okay, good afternoon, everyone. So, firstly, sorry about all the confusion today. My daughter was going through surgery and it ended up being considerably longer than expected. So, I had to wait for her discharge. So, thanks for understanding. Um, anyway, let's jump right into business. So, firstly, hopefully, you all saw my announcement about the quiz date, and also hopefully you have started on um, the PSET. The quiz will include all the material through today's lecture and this week's discussion section and next Tuesday's discussion section, because as you know, the Tuesday section covers material from the preceding week. Okay, so any questions on that before I start on the main lecture? Okay, and again, please speak up instead of writing on the chat. So that way it's easier in case you have a question for me to answer. Otherwise, I often end up missing them. So please do that. Okay, so last time we saw how to design combinational logic circuits using Carnot maps and kind of the whole idea of prime implicants, essential prime implicants, and so forth. And we also talked about the limitations of Carnot map, namely they only give us logic which is two-stage, as opposed to logic which is with more general logic. But more importantly, a lot of times we implement combinational logic which has some structure to it. There is some pattern to it, and therefore doing it the Carnot map approach often tends up being very, very inefficient. Like, for example, let's say you are designing an adder. Then if you know how to do 4-bit adder, then the 5-bit adder follows the same pattern, right? I mean, you add one, you kind of repeat the approach that you did for the first 4 bits. And there are many examples like that where there is this kind of a structure, and it would be good to exploit it and then reuse it, as opposed to every time we face a combination design problem, feeding it into some sort of a Carnot map or analogous approach. So we see that in software also. Every time we face a problem, we don't just write from scratch. We have libraries of software functions, and we try to exploit those. So that's the spirit here, which is we are going to see what goes into a library of combinational functions, which we can then use as building blocks to do other stuff. So just like in software, libraries may include mathematical libraries or various other kind of functions. It's the same approach here. By the way, just to check, you guys are able to hear, right? I mean, nope, no one there?
Yeah, we can hear you.
Yeah, we can hear. Okay, yeah. There was utter silence. I just wanted to make sure that there's no connectivity issues. Thanks. Okay, so what we are going to do in this module is to look at what some of those building blocks are. In software, like we have libraries of mathematical functions, signal processing functions, those kind of things. There's analogous things out here that over the years people have found to be useful as combinational building blocks. Okay, so so that's the theme, and in particular, we are going to cover the combinational logic blocks listed out here, something called decoder, encoder, multiplexer, arbiter, comparator. These are, you can think of them as the idioms of digital design. That is, we try to break more complicated combinational logic in terms of these. So as opposed to going all the way down to NAND gates and OR gates and AND gates, which are very, very simple in terms of their functionality, here we kind of, it turns out that these components tend to play an important role. Okay, so let's start with those. So decoder, encoder, multiplexer, arbiter, comparator, and then we're going to look at something called ROM, or read-only memory. So what's a decoder? Now, English meaning of decoder is that we take some piece of information and we decode it into something which is simpler to understand, right? So what a decoder does is the following. So imagine you have n things, and I can represent those n things in log to n bits, right? So if I have 8 things, then I can represent them in 3 bits, and that's the most compact coding. But there is also the one-hot representation that we saw, where if I have n things, I represent them using n bits, and kind of the idea being that bit number 0, if we count bits from the right-hand side out here, so like, for example, pair out here, bit number 0, that represents the 0th entry in our set. So essentially, think of, like, let's say the set that we had was digits from 0 to 7, the decimal digits is value 0 or 7. In binary, we represent them using kind of the base 2 representation, right? So 6 is 110 because it's 4 plus 2 plus 4 plus 2 plus 0. Or I can represent it in this one-hot manner. Okay, and we've seen this earlier. Okay, so there are 2 different ways of representing the same thing. What a decoder does is it converts symbols from one encoding to another. Okay, so same set of values, they have 2 different encodings, and a decoder goes from usually a more compact encoding to a more sparse encoding. And in particular, the one which we are interested in is it takes binary representation, the things which are in the form of a base 2 number, and outputs a one-hot representation. So, for example, if I have 8 things, then the binary representation would be 3 bits, and one-hot encoding would be 8 bits, right? So, or more importantly, if I have an n-bit base 2 number, then in one-hot coding, it would be 2 to the power n. Is what we would have. So let's look at an example. Okay, so that's what we want to achieve. So what we basically want to do is we want to basically say that if input A has the value I, right? So if I think of the input A in terms of like a base 2 number, then the ith bit of the output B is set to 1, and all the other bits are set to 0. Or equivalently, if you're familiar with programming languages, I can say that if I think of B as a number, right, because B is also a set of bits, then B has the value given out here, 1 less than A. Anyone knows what this stands for in your languages like C++? Left shift, right? So it's basically saying take 1 and shift it left A times, right? So if A is 0, the rightmost bit would be 1 in B. If A is 1, the second from rightmost would be 1, and so on and so forth. And as you can imagine, that is exactly the one-hot coding. So mathematically, a decoder is basically doing this operation. If I think of A and B as numbers, then it's basically saying B is 1 left shifted by A. Or the bit string, the sequence of bits in B is obtained by taking the number 1 and left shifting it by A. Or alternatively, we can write it like this, that if A is I, then the ith bit of B is I. Ith B of bit is 1. Okay, so that's what we want. Let's take a specific example. This one was abstract. So let's say I'm trying to create a 2 to 4 decoder. So a 2 to 4 decoder will take a 2-bit binary value, and it will output a 4-bit one-hot encoding, right? Because 2 bits on the input, 2 bits of binary value can represent 4 things. So I need a one-hot encoding of 4. So how do we implement such a system, right? And then we'll show that if you can implement something like this in the general case, then I can use that as a building block. So to implement this, I can use the truth table approach, except now I have 4 outputs, right? Because output B is 4 bits. So B0, B1, B2, B3, and I have 2 bits of input, A0 and A1. So if A1 and A0 are both zeros, then B0 will have to be 1, and all the others would be 0, right? Because 0, 0 represents 0. If A1, A0 is 0 and 1, then B1 has to be 1. So that's what the output would look like. If A1, A0 is 1, 0, then B2 would be high. And then finally, if A1, A0 are both 1s, then B3 is high. So that's a truth table. And then looking at this, I can implement B0, B1, B2, B3. There, essentially, I have, you can either think of it as I have 4 different functions corresponding to B0, B1, B2, B3, or alternatively, I can think of I have a single function with 4 bits of output. So what would the expression for B0 look like? Well, if I focus on that column, then it seems it's A1, A0 is 0, 0. That's when it is 1, otherwise 0. So what do you think is B0? How can I express B0 in terms of A1 and A0? So like if you were to implement B0 using some gate or gates, what function of A0 and A1 is it?
You could do like not A1 and not A0.
Okay, and then AND them, true. And what is that? If I'm complementing them and then ANDing them, what is that gate called? Right. So what is
that the same as a NOR?
Same as NOR? Right. So basically we have a NOR gate there. Likewise for B1, B2, B3. B3 is just an AND gate, as you can see, right? So I can implement these 4 functions. So one way I can do is basically I can create all the minterms. So B3, for example, is A0 and A1. B2 is A1 and not A0, and so on and so forth. So this circuit implements all these 4 bits. So that's hopefully seems simple enough. The problem though is that if I have to now, let's imagine if I have to create a very large decoder, and oftentimes decoders are very large, right? I mean, if I have to create a 3 to 8 decoder, that's larger still, 4 to 16, 5 to 32, 50 to 2 to the power 50, right? I mean, I may want to create large decoders. So what we are going to see is that how we can use small decoders to build large decoders. But 2 to 4 is simple enough that this is how we can do it. So now let's say we want to create a larger decoder, 6 to 64, right? 6-bit input, and so I will have 2 to the power 6 or 64 bits of output. I can certainly attempt to do it using Karnaugh map, but it would be a painful exercise because I'll have to implement 64 different outputs, right? So I'll have to essentially solve 64 different Karnaugh maps of 2 bits. So the idea here is that perhaps if I have available to me smaller decoders, could I combine them to create bigger decoders? A little bit like in software when you learn about recursive functions, right? If I have like, for example, factorial n is n times factorial n minus 1. So I can make a bigger factorial in terms of smaller. If I know how to implement a smaller factorial, then I can bigger one. So same kind of concept. Okay, so let's first see what is a 6 to 64 decoder. Well, the 6 to 64 decoder would have n equal to 6, and output would be m equal to 64, right? So that's so we could do it the way we did 2 to 4, but a better option may be that since we already know how to do 2 to 4, can I use that as a building block? Instead of building block being NAND gates and NOR gates, can I use the decoder which we have already designed, 2 to 4? Can I use that to create 6 to 64 more easily? So that's what we're going to look at. So kind of the idea is that if I'm trying to design 6 to 64, so I can think of my 6-bit input, A going from 0 to 5. I can think of them in groups of 2. So A10, A32, and A54. This syntax A5:4 means A5 and A4 together, right? A32 means A3 and A2 concatenated, right? So imagine that I chop my input into groups of 2. And then each group of 2, I can decode using my 2 to 4 decoder, which I've already designed. And let's imagine the output of those decoders are called X, Y, and Z, and they will be 4-bit each, right? Because it's a 2 to 4 decoder. So I take that 6-bit input, chop it into 3 groups of 2, and decode each one of those groups of 2. Okay, so essentially, this is a situation that we will have. I take 6 bits of it, A, chop it up into 3 groups of 2, identified by the red blocks. Within each group, there are 2 bits, A0, A1, A2, A3, A4, A5, as I go from right to left. It's conventionally, we always write the 0th index to the right. So our 2 to 4 decoder would yield a truth table like the one we saw a couple of slides ago. So each one of these, we have the 3 truth tables. So whenever A0, A1 is 0, 0, then imagine the decoder which is decoding these 2 bits. Actually, there's a typo out here. This should be X. So the 4 bits of X would look like 0, 0, 0, 1, and so on and so forth. The middle group leads to 4 Y bits, and the leftmost group leads to 4 Z bits. So after this initial stage, the 6 bits of A are now 3 groups of 4, so a total of 12 bits. Okay, no cigar still, right? Because what we are interested in is getting to row 64. But let's see how we can pull that off. So how to get the 64 from the outputs of these 3 groups. So the idea out here is the following. So step 1, we have done what we showed. In step 2, we kind of recognize that the information in A1, A0 is captured in X3, X2, X1, X0. Likewise, all the information is A3 and A2 is captured in Y, and all the information in A5 and A4 is captured in Z, right? Because I could certainly, they're both representing sort of 4 things each, right? A1, A0 can capture 4 elements, so can X. So it stands to reason that if B is a function of A, then I can equivalently express B in terms of X, Y, and Z, right? So for example, if all the A's are 0, by the way, keep making the same correction, like on the rightmost grip is all X, okay? This is a consistent, because of animation, the error is repeating. Okay, so if B were to be all 0, then, sorry, if A were to be all 0, then B0 will be high, and all the other 63 Bs would be 0. But if A is all 0, then we know that Z0 is high, and Y0 is high, and X0 is high. So we can say that B0 is going to be high, right? I mean, B0 is high if A4 and A5 are 0, and A2 and A3 are 0, and A0 and A1 are 0, right? So I can write like this. I can say B0 equals to 1 if A1 colon 0 is 0, 0, and A3 colon 2 equals to 0, 0, and A5 colon 4 is 0, 0, which is the same as saying, is equivalent to saying A1 colon 0, 0, 0 is the same thing as saying, X0 is high and Y0 is high and Z0 is high. So I can, for the output B0 out here, I can start with its expression in terms of A, but I can translate that into an equivalent expression in terms of X, Y, and Z. And that's the game we are going to play. That for each one of the B, it represents some combination of one of the Z's, one of the Y's, one of the X's. So for example, let's say I'm looking at B63, right? B going from 0 to 63. So if I'm looking at B63, then that happens when all the A's are 1. And looking at our table, that would mean that Z3 is high, and Y3 is high, and X3 is high. So that would be kind of the idea, that I take the index of B and translate them into some combination of X, Y, Z. So let's see how it kind of works out. So consider BI, right? So we are looking at the ith bit of the output. So BI is going to be 1 if A had the value I, and otherwise BI is 0, right? So if A represented the number I, the bits of A represent the number I, then BI is 1, otherwise BI is 0. And this we can translate, like the two examples I showed, in terms of some expression of one of the X's, one of the Y's, one of the Z's. So I equal A being I means that the bits of, let me try to explain it differently. Yeah, actually, yeah. So let's take another example. Okay, so that, let's say I'm looking at B1. So when is B1 high? Well, B1 is high if A 5 colon 0 is 0, 0, 0, 0, 0, 1. And now we look at these groups of 2. So this is saying the first one is saying A5, A4 is 0, 0. A5, A4, 0, 0 means Z0 is high. So this is same as saying Z0 is true. Next group being 0, 0 corresponds out here. So that means Y0 is true. And then finally, again, the same typo, which is repeated out here. X0 is 0, 1 means we are here. So that means X1 is true. So it's going to be the ending of these 3 terms.
Quick question.
Yeah, go ahead.
So where are you getting the 64 bits from? Because it's like 12 in this case, right? If you
no, A is 6, right? So this is 6 here. So the definition of decoder is I'm going from 6 to 2 to the power 6.
Yes, so
that's what I'm writing.
Where in the output do you get the 2 to the 6, like in your example?
Well, this is 64-bit. So this is 64-bit.
Oh, okay. Never mind.
Right,
Okay,
right. So I'm taking a 6-bit binary number and I'm converting into one-hot coding, which will require 64 bits, right? So the B has 64 bits.
Okay.
So now imagine A was high. A was A had the value I, then I can look at, so A is 6 bits. So I can now look at, let's say, the upper 2 bits of A, which are bits 5 and 4. And I look at those values, right? So bit 5 and 4 can take 4 possible values. They could be either 0, 0, or 0, 1, or 1, 0, or 1, 1. And depending if A5, A4 is 0, 0, then Z0 is 1. If A5, A4 is 0, 1, then Z1 is 1. If A54 is 1, 0, then Z2 is 1, as you see out here. And finally, if A54 is 1, 1, then Z3 is 1. So I can basically say that I equal to A means that Z, there is funny notation out here, right? I mean, so Z has 4 possible indices, 0, 1, 2, 3. And basically, A54, those 2 bits tell us which Z we care about. So if A54 is 0, 0, then I, which is the value of A, is also, I is just equal to A, right? I mean, so this kind of follows from that. So if A54 is 0, 0, then Z0 would be 1. If A54 is 0, 1, then Z1 will be 1, and so on and so forth. So this expression is basically just expressing that fact, which Z is 1. That depends upon the bit number 4 and 5 of A. Sorry. Okay. And same thing will be true for the middle 2 bits, bits 3 and 2, and then the rightmost bits, 1 and 0, except that these bits map to Y and these bits map to X. So if, sorry. So if I has the value A, then that is the same thing as saying X indexed by the lower 2 bits of I is 1, and Y indexed by middle 2 bits of I is 1, and Z indexed by the bits 5 and 4 is 1. So in particular, if let's say the value, so I is the value that we are feeding out here, right? So let me erase this thing for a moment. Yeah, it doesn't work. Okay, so if A is getting the value I, then depending upon what the bits of I are, we get to know which X and which Y and which Z are 1, and the remaining, exactly one of the 4 Ys will be 1, exactly one of the 4 X's will be 1, and exactly one of the 4 Z's would be 1. So, and that is dictated by the bits that are being received by A. And so I can write that as an AND expression. So for example, which I've been doing, right? So if I'm interested in B0, then that is the same as saying X0 and Y0 and Z0, right? Because it corresponds to the pattern that all A should be 0. So each one of the 64 bits of B will correspond to some combination of Z, Y, and X. And that stands to reason because I have 4 possible cases for Z, 4 possible cases for Y, and 4 possible cases of X. So 4 times 4 times 4, that's 64 also, right? So there are, so if I, so think of it like you are allowed to pick 1 Z and 1 Y and 1 X. There are 64 such possibilities, and each one of them corresponds to one of the bits of B. So that's what is happening. So implementation wise, it looks like this now. I take my bits of A, I chop them into 3 groups of 2, feed them into the 2 to 4 decoder, which we have previously designed. Then I get 4 bits of X, which is the leftmost vertical line, right? X30, 4 bits of Y, which is the middle group, and 4 groups of Z. And then I combine them in all the possible 64 manners, right? So I can say, let's take x0 and y0 and z0, that becomes b0. If I take x1, y0, z0, that becomes b1. And final, all the way up to, if I take x3 and y3 and z3, that would be b63. So whichever b you pick, there would be a corresponding combination of x, y, and z, which will achieve that objective. So the recipe out here is I take my inputs, chop them up, feed them into smaller decoders, and then take the output of those decoders and create all possible combinations. So for example, let's say magically, if I had a 3 to 8 decoder, or I had 3 to 8 decoders, then I could have implemented the 6 to 64 decoders by taking my A, chopping it up into 2 groups of 3 bits, feeding them into 3 to 8. Then I will get, let's say, x, 8 x's, and right. So I could have done something like this, right? So I can take A5 colon 0, I can split it into A2 colon 0, A5 colon 3, feed them into 3 to 8 decoders. Let's say I had those. Then I will get x 7 colon 0 and y 7 colon 0. And then I can combine these things using AND gates, right? And there will be 8 times 8, 64 possibilities, right? So x0 and y0, ANDing them together will give me b0, and combining x7 and y7 will give me b63 and everything in between. So I could take smaller decoders like this, chop my input correspondingly, and map these things this way. As I will shortly show, this actually gives holds advantages as opposed to going the Karnaugh map approach, where you are going to create things all the way down into 2 levels of AND and OR, right? Let's think about this circuit that I have just shown out here. Within the 2 to 4 decoder, we already have 2 levels of logic, right? We saw that. And then we are combining them. So this circuit we are seeing actually has a depth 3, right? If from input to output, we go through 3 gates, 2 within the 2 to 4 decoder, and then finally this AND gate. So this is already an example of something which is no longer sum of product or product of sums. It is something more complicated. But it simplifies our life, right? We design a smaller piece, and then we create bigger things out of it. So let's think about what a direct implementation of 6 to 64 might look like. How many gates would I need if I were to implement 6 to 64 decoder directly in terms of AND and OR gates? So we saw 2 to 4. In 2 to 4, we needed 2 NOT gates, and we had needed 4 OR gates. For 6 to 64, how many gates are needed? Anyone? How would you implement directly, just using AND or NOT, a 6 to 64 decoder? So I have to create all possible 64 combinations of the 6 inputs, either directly or the inward. So I would need 6 NOT gates. I'm going to just write it down here. Let's see. So sorry. So I would need 6 inverters to possibly invert each input. And then I will take, for each input, I will either take the input or its inverted version, and I am going to then AND them. And I will have 64 AND gates, and each one of them would be taking 6 literals. So I will need 64 AND gates of 6 inputs, and I will need 6 inverters. That is if I were to directly implement the 6 to 64 thing, right? Much patterned exactly after 2 to 4. How many gates do we have out here? Let's check that. Using this implementation using 2 to 4 gates, I need 64 AND gates, but they are of 3 input each. And I need 3 2 to 4 decoders. How many gates does a 2 to 4 decoder need? We saw that. Anyone? What did we have in the 2 to 4 decoder implementation? So I have 2 bits out here. So I will need 2 NOT gates. Plus 4 2 input AND gates. And I need 3 such things. Plus the AND gates out here. So the overall cost would be 64 and 3 plus 3 times, because I have 3 2 to 4 decoders, 4 and 2s, 4 2 input AND gates, and 2 inverters. I add them together, I'll get the total cost. Which one do you think is more expensive? Now they have the same number of inverters, so they get chopped out. I have 64 3 input AND gates and 12 2 input AND gates versus 64 6 input AND gates. 64 6 input AND gates is a lot more expensive. Its cost is 64 times 6, whereas the cost of the lower one is 64 times 3 plus 12 times 2, 24. Okay, so a lot cheaper, the second solution. It has fewer literals, fewer. If I count the gate inputs, it has fewer inputs. So this solution is certainly lower area. What about the speed? Well, it's going through 3 levels of logic, right? Because 2 within this and then this, right? So if I count how many stages of logic gates is going from input to output, this one is this new solution is going through more stages. So maybe it has bigger delays. That part is less clear because as gates get delay depends not only on how many stages of gates you're going through, but also how big those gates are. So an AND 6 is going to be a lot slower than an AND 3. So even though I'm going through more stages of logic gates in this new solution, I may actually still be faster. So gate complexity is certainly lower in this new solution, and speed is a little bit less clear. It may be higher, maybe lower, depends. Okay. Generally speaking, if your delays depend only on how many stages of gates you have, then the direct Karnaugh map implementation or that kind of implementation, sum of products or product of sums, would be faster. But devil is in the details there. So to summarize decoders, kind of the idea is that you may be given smaller decoders and you can combine them to create bigger decoders. So if I give you, for example, let's say a supply of 2 to 4 and 3 to 8 decoders, then I ask you, make a 5 to 32 decoder. Well, I could do it using 1 2 to 4 decoder and 1 3 to 8 decoders, because I'll take my 5-bit input, I'll chop it up into one group of 2 and one group of 3. The group of 2, I will feed to the 2 to 4 decoder, expand it into 4 bits. And the group of 3, I will feed to 3 to 8 decoder, expand into a group of 8 bits. And then 8 times 4 is 32. So I will take all possible combinations from that group of 4, let's call it X, and group of 8, let's call it Y. So I'll combine those in all possible ways. So that's how we make a decoder. And actually, if you think of it's kind of like a decision-making process. if I present to you that take A and then take some action depending upon what A is, and if A is 6 bits, so it has 64 possibilities. So I can kind of do it in one go. I can think of like a flat decision. I can think of it like, if A is 0, 0, 0, 0, 0, do this. If A is 0, 0, 0, 0, 0, 1, do something else, and so on and so forth. So I can think of it like a if then else type system, which has 64 different branches. Or I can say, first, let me look at the first 3 bits of A, and that will give me 8 cases each. And then within each case, then I look at the remaining 3 bits and I will have 8 subcases. So if you think of it in terms of those like a decision-making process where I have a single stage decision from A to all the cases of B, or I can do it in multiple steps. That's what's going on. Decoder is like if then else, right? That's what's going on. So let's think of how you might create. Now that we have a 6-bit decoder, I can make a 12-bit decoder. I can take 2 6-bit decoders together with some AND gates to make a 12-bit decoder. I can also, so basically kind of the part which you need to become comfortable with is how can I take smaller decoders and bigger ones. So this one we already saw that I can make 6 to 64 using 3 to 8, that we already saw. So why decoders? Like, why am I spending so much time over decoders? It turns out that in digital systems, decoders play a very important role, because oftentimes we are faced with the situation that I have a group of bits, and depending upon what those group of bits have, I take a different action. It could be, which sensor do I read the data from? So I may have 3 bits, 8 sensors. The 3 bits tell me which sensor to get the data from. Or it could be which motor to turn on. Again, I'll take those 3 bits. Very commonly though, most common use is that addressing memory. So I may have some sort of a memory chip in which there are lots of locations, and given an address, I need to read one of those locations. So my memory chip may have, let's say, 256 slots. So 256 slots means to address those slots, I need 8 bits, right? To the power 8 is 60, it is 256. But once I have the 8 bits of address, then I have to go and inside the circuit turn on one of those slots so that I can read the contents of that slot. So that's an act of a decoder. So if you look inside the memory chips that are used in our computers, they actually have gigantic decoders inside it. And typically, the memory chips, the slots in the memory chip, they're not organized as a single array. They're organized as a 2-dimensional array. So for example, this little chip that you are seeing is an example where I have 16 locations. So I would need a 4-bit address for that, right? Except what we do out here is, because we like to create chips which are well-shaped, so I lay the memory cells in a 4x4 matrix. 4 rows, 4 columns. Then at each location, we have 4 bits. So I have 16 locations of 4-bit each. Importantly though, the address that we are getting, which is represented as MAR, memory address, we split it into 2. 2 bits go on to select which column, and 2 bits go on to select which row. And how do we select rows and column? You see a little friend decoder out here, 2 to 4 decoder and 2 to 4 decoder out here. So memory chips are one place where decoders are used. And of course, our memory chips are gigantic. Nowadays, you get DRAMs, which are the DIMMs that you put in your computer, and they have, I don't know, 256 gigabits. That's so if you think about it, how many address bits do I need for 256 gig? Well, 32 bits give us 4 gigs. So 256 would give us an additional 6 bits. So I will need 38 bits. So I have memories which have like really large number of address bits. And even if I do this row column game, I have 2 to the power 19 rows and 2 to the power 19 columns. So decoders inside memory chips can be really gigantic. Okay, not like our 2 to 4 and 3 to 6, 3 to 8, much bigger. So that's one place decoders are used. Decoders are also used in displays. So probably you are watching this lecture on your laptop. Laptop has a display screen. Display screen is organized as an array of pixels. Accessing those pixels, so when the software changes or paints something on the screen, it has to select certain pixels to draw upon. And again, that is where it uses decoders. You may have seen in your calculators displays which look like in the bottom part of the screen, right? Using little LEDs, they make different numbers, for example. So these kind of displays basically are composed of 8 LEDs, as you can see from the number 8. 7 LEDs. So the digit 8, you see 7 little segments. So these displays have a bunch of digits, and each digits have 7 LED segments. And so when you display on these calculator displays, you have to turn on or off at each digit position the appropriate LED segments. And so this is often called as binary coded decimal to 7 segment display decoder, right? Because we display digits 0 through 9, and depending upon what the digit is, we have to turn on the right segment. So this table is an attempt to show that. So like, for example, let's say I want to display the digit 2. So if you look at the digit 2 here, you see A, B, E, D, and G, those segments are on. So if you look at the table, the entry for 2, you would see that A, B, so for 2, you see A, B, D, E, and G are turned on, and that is what you see out here also. So for each digit, 0 through 9, and if actually you're displaying hexadecimal digit, then usually they do A, little b, C, little d, E, and F. So corresponding to the input would be 4 bits, telling us which digit, and output is 7 bits, telling us which LEDs are on. So that's another example of a decoder. So decoders are abundant in real life usage. Now, a nice thing about decoder is that actually, if you have a decoder, then you can implement any function. So what if I told you that was the case? If I said, previously we have seen that if I gave you NAND gates, you can implement any logic. If you have and, or, and not, you can implement any logic. What if I told you that if I gave you decoder, then you can implement any logic? Specifically, let's say I told you that given an infinite supply of 2 to 4 decoders, you can implement any logic. Why do you think it might be the case? And you think of how you might go around doing it, right? So firstly, if I gave you 2 to 4 decoders, you can implement all sort of other decoders. But let's start with So using 2 to 4 decoder, what games can we play? So let's think about it. A decoder, one way of thinking about the decoder is that it is telling us which minterm is true, right? So if I had a 2 to 4 decoder, then if both A bits are 0, then B0 is high. If A1 is 0 and A0 is 1, then bit 1 is high, and so on and so forth. So one way of thinking about it is selecting which row of your truth table is true, right? If I have a n-bit function, then I can use an n to 2 to the power n decoder, right? So if I have n-bit function, that is, it takes f x a n minus 1 to a0, right? So if you think of the truth table for this guy, it will have 2 to the power n rows. So you can think of the decoder tells us each output of the decoder corresponds to a different minterm, right? B0 is true when it's 0, 0. B1 is true when it's 0, 1, right? So it's basically telling us which minterm. And then we already have seen that I can implement any function using an OR of minterms. So I guess I wasn't quite truthful. Decoder together with an OR gate, I can implement any function. So for example, our good old friend, a 3-bit 1 OR prime function can be thought of as I take my 3 bits of input, decode it, I get 8 bits on the decoder, and then I select those entries which correspond to the minterm I'm interested in. So 1, 2, 3, 5, 7, I put an OR gate out here. So decoders plus OR gate can implement any logic. Not a very efficient way of doing it. What do you think is bad about the design that I just gave for the S prime? I mean, it certainly implements S prime, but what do you think is the problem with this design?
Is it harder to get like a simplified version? Because usually with minterms, you're able to like simplify it into a couple less terms, right?
Yeah, I mean, I'm not sure we're saying the same thing or not, but yes, it's inefficient. It's inefficient because I'm computing some minterms and I'm not using them, right? B0, B4, B6 are not being used, and yet the decoder outputs those also, right? So decoder is creating 8 intermediate values, but I'm only using 5 of those. So it's not very efficient, but it's general. So if I gave you a supply of decoder and OR gates, then it kind of gives me a general way of doing things. So this style of logic, where you had a decoder and then combined using an OR gate, used to be very popular in early days of digital systems. Even now, those chips exist in low-end systems. Basically, they're called things like programmable logic arrays and all, but they would allow you to they'll put a mass of decoders and they'll put a highly programmable OR gate. Okay, so essentially you take a decoder, look at all its output, and then you can tell the OR gate which one of those outputs to look at. And that's how they would achieve a general way of doing things. Okay, so if we have decoder, we are also going to have encoder. And encoders do exactly the opposite. They go from one hot to binary. Decoder went from binary to one hot. So encoder goes one hot to binary. It's the inverse of a decoder. So encoder is a logic module that converts a one hot signal to a binary encoded signal. In particular, instead of a 2 to 4 decoder, now I have a 4 to 2 encoder. So it takes 4 bits in a one hot format and converts them into a 2-bit representation. So it's a function with 4 inputs and 2 outputs. what do you see interesting about this truth table? Have I fully specified it? So let's say if A3, A2, A1, A0 were all ones, what do you think should be the output?
You ignore it.
Yeah, you'll ignore it because it's not a valid one hot code, right? Like with all zeros. So there has to be on the input, there has to be one, exactly one, right? And the rest 0, 3 zeros and 1, 1. So everything else should be a don't care. You don't care about it because it should not occur. We'll see an exception to it shortly, but that would be kind of the idea. So I can implement the circuit using a Karnaugh map very easily. It will look something like this. The remaining, in this case, 12 rows are don't cares, but this is an implementation. There are obviously other possible implementations also. So like, for example, if we look at B0, then B0 is 1 when A1 is 1 or A3 is 1. And so that's what we are seeing out here. And likewise B1. And here we are making the assumption that the other, it should only valid one hot codes will be seen. So I don't have to worry about what's happening in the other rows because we don't care. Okay, so very simple implementation for this encoder. As you can also see, A0 plays no role. Okay, because again, this is because we know we are given the requirement that the input is one hot coded. So A0 is not being used. It is disconnected. It doesn't matter, okay, given the problem specification. So the problem out here is that what do we want if the input is not one hot coded? So one stance we can take is, hey, you told me to design an encoder. You told me that I should go from one hot to binary encoded. So you better present me a one hot input. If you don't present me a one hot input, I can produce some junk value. But an alternative perspective could be say that, I need to be cautious. If the input is not a valid one hot code, then I'm going to produce some sort of an error signal. Okay. So depends on the perspective you take. So we'll see shortly that it turns out useful to have this kind of an error signal. So in particular, we are going to add a signal, and which we'll shortly make use of beneficially, that if all the inputs are 0, we are going to indicate that. So I have a signal V at the output. We are going to add that, and it basically is going to output 0. It basically indicates whether all bits of input are 0 or not. So in particular, I'm going to OR them together. So if all the 4 inputs A0 through A3 are 0, then V is 0. Otherwise, V is 1. And we'll see shortly a use for this thing. So just bear with me for now. So usually we implement encoders so that they also have this V bit. And the reason we do it is same reason we something that we saw with decoder, which is we want to create bigger encoders from smaller encoders. So that's what we are going to do. So let's say, so we already saw how we can design a 4-to-2 encoder. That was super easy. But now let's say I told you I want to design a 16-to-4 encoder, right? It's going to take a 16-bit one hot representation, and it's going to produce 4-bit encoding of that, right? Because log2 of 16 is 4. So what we are going to do is the following. I'll have that 4-to-2 decoder that we just built, but it also has that V signal. And that V signal is going to be represented by the red lines out here. Okay, so the red signals tell us it is 0 if all the inputs are 0, and it is 1 otherwise. Okay, so this circuit that we have helps us create this larger design. So like from 4 to 2 to 16 to 4. So how does it work? So remember the V line, again, going back out here, the V signal is high if one of the inputs is high, right? And we know exactly one input will be high, right? So one of the A's is high, and V is 0 if it so happens that all the A's are 0. So now what will happen out here? So let's take the circuit. The input is 16 bits. How many A's will be, how many of these 16 bits will be 1? So if I look at A, I divide A into 4 groups of 4. But if I look at the whole thing, how many of these A bits are 1?
4.
4. Why?
Because you have oh wait, sorry, 5. I mean,
5. Why?
If you have
what does it say out here? 1 hot. Input A is 1 hot. So how many bits of A will be 1?
oh, just 1 then.
Just 1, right? Okay, so one of these A bits is 1, but that 1 bit could be in any one of these 4 groups. It has to be in one of those groups, but one of those 4 groups. So let's say A11 was high. Then the upper and the lower 2 red decoders, their red line, which is the V line, is going to be 0 because they are going to see all zeros in their input. Whereas the red output of this guy is going to have a 1 on it because it is seeing a 1 in it. So the red line is telling which one of the 4 groups has the A bit which is 1. Right? So if AI is 1, then which one of these 4 groups has that AI? That's what the red line is telling us, right? Well, the red line is 0. As per the previous slide, it is 0 when all the inputs are 0. And what is blue line telling us within each group? It's telling us which one of which of the 4 bits in that group is high, right? So if red line is 0, which means that group should not matter. And if red line is 1, then we care about that group. So we use these 4 to 2 decoders to identify which group of 4 has the 1 bit in it. And then we take those red lines, feed them into a 4 to 2 encoder, and that outputs the upper 2 bits for our design, right? Upper 2 bits of encoder, because the upper 2 bits are going to tell us where the 1 bit is. So we'll see an example shortly. And we take the blue lines, which correspond, which are telling us where is it that the 1 bit occurs within the group. And if the 1 bit doesn't occur, then blue lines are all zeros. Then I feed them into this OR gate. But this is a funny OR gate. If you see, this OR gate has 2 bits. Each input is 2 bits and each output is 2 bits. You can really, so oftentimes out of convenience, what we do is the following. Let's say I'm trying to write following. Let's say I'm trying to implement this. This gets very clumsy if I have lots of bits. So oftentimes we write it like this. So that's what you're seeing out here. You're seeing 2 bits here, 2 bits here, 2 bits here, 2 bits here, 2 bits here. So what it is really saying is that this OR gate is really 2 OR gates. One of them is ORing the bit number 0 for all the inputs and producing bit number 0 of the output, and the other one is producing the other bits. So I'm basically taking these blue lines, 3 of them would be all zeros because they did not see a valid one hot output, and one of them would be either 0 0 or 0 1 or 1 0 or 1 1. So I OR them together. That one essentially is passing through, and I'm going to get the lower 2 bits out here. So I know this is pretty abstract, so let's look at an example. So again, the behavior of 4 to 2 encoders, the special 4 to 2 encoder is that if it sees all zeros, then the red line is 0 and the blue line is 0. If it sees a valid one hot code, then red line is 1 and blue line has the appropriate encoded value. So with that for type of 4 to 2 encoder, let's look at an example. Yeah, this I already described that. That's the special notation for OR gate. So let's look at an example. Let's say A9 was high. So remember, A is one hot coded. So let's say A9 was high. So that means A9 is what we are after. So if A9 is high, then this group is the one which is seeing A9. So it will produce on its red line of 1. All the other are going to be 0. So these are going to be 0 because they A5 through 12 is all 0, A7 to 4 is all 0, and A3 to 0 is all 0. So that's what we are going to see. So that's what we are seeing on the upper decoder at the output. And since this is 0 0 1 0, then what we will see on B32 is 1 0. Furthermore, A9 is 1. So A9, so A11, if I look at A11 to A8, it would look like 0. Sorry. So A11 to 8 would look like 0 0 1 0. 0 0 1 0 means bit when encoded, it's value 1, right? Because bit position 1 starting with B0, bit 0, 1, 2, 3. So the output would be 0 1. So the blue line for this decoder, this encoder would be 0 1. All the other blue lines are going to get 0 zeros. And now when we combine these outputs, the OR gate would produce 0 1 and the upper end would produce 1 0. And if you think of it, it's 1 0 0 1, which is 9. So A9 results in that.
A quick question.
Yeah, go ahead.
So the input to the blue line itself is like encoded in terms of like ordering.
Could you repeat the question again? The input of
input to the blue line, like it's also like encoded in some sense.
they are the binary encoding, right? I mean, so encoder goes from one hot to binary, right? So which is why if A9 was 1, then this encoder was seeing 0 0 1 0. 0 0 1 0 is 1 hot for 1. Right? So that's why it is producing 0 1. So think of this 0 1 as a binary value 0 1, right? So it has a value 1. Let's say, for example, let's say hypothetically, let's say A10 was 1, not A9. In that case, we would have seen 0 1 0 0. And in that case, I would have seen 1 0 out here.
Okay. What about in the case of like A0, where both of them are just 0 0?
What about the case of
like
A0?
Yeah, so where B1 and B0 are like both 0 0, but you still have like the one hot encoding.
Okay, so let's say A0 was high. Right, so I will be seeing 0, 0, 0, 1 here, and I'll be seeing all zeros everywhere else. So this red line would be 0, this blue line would be 0, 0, this red line would be 0, this blue line would be 0, 0, this red line would be 0, this, yeah, I see what you're saying. So what will happen if where we are headed? Okay, so what will happen now? So we'll have 0 here, we'll have 0, 0 here, we'll have 0 here, we'll have 0, 0 here, we'll have 0 here, and we'll have 0, 0 here. But this guy will be 1, and this guy will be 0, 0, 0. So now the decoder would see 0, 0, 0, 1. And hang on a second. So all 0, am I messing things up? So this one is going to see 0, 0, 0, 1 out here, right? 0, 0, 0, 0, 1, and therefore it is going to output 0, 0. And this one is seeing all zeros everywhere, so it will also output all zeros. So we will get a 4-bit 0, 0, 0, 0, which is what you want, right? Because A0 was 1.
Cool, got it.
Okay. Okay, so that's the idea out here. So for encode, we can again make bigger encoders from smaller encoders, provided we play this funny game of creating this extra output, which indicates whether we are seeing a valid one hot coded input or not. So why encoders? And decoders were obviously useful, we saw. Encoders are also very useful. Encoders are used whenever we want to take something which is one hot coded and then reduce the size of representation. So let's say I have 100 cameras and they are that's a bad example. Let's say I have let's stick with the example. I have keyboard. So we press key at a time. So whenever you press a key, the corresponding line becomes 1, right? Deep down, there's some electrical circuit. And so when we press the key, the circuit closes and that line becomes 1. So if I have a, let's say, 100 key keyboard, I have 100 lines. At any given point in time, one of them is 1. But instead of sending 100 bits to the computer, to the CPU, I want to reduce them down, let's say in our example, to 7 bits, because 7 bits can represent 128 values. So I'm going to use an encoder to go from 100 to 7. So anytime you are faced with large vector where representing some sort of a selection of a key or a sensor or something like that, and then I want to reduce it to address for that sensor, right? I mean, so key, you can think of like when I'm going from which key is being pressed from one hot to an encoded value, I'm really coding up the key in some compact representation. And which is why I'm sure you may have heard of like computers represent alphabet in terms of something called ANSI code, which is a 7 or 8-bit code. And that's an example, right? I mean, so keyboards, when they talk to the CPU, they are not sending, if they have 100 keys, they're not sending 100 bits to it. They're actually sending 7 or 8 bits to it. Okay, so that was encoder. We are pretty close to the end time, but just to do a little bit of a peek ahead, the next module we are going to cover is multiplexer. And multiplexers are used anytime we need to select a data source. So imagine I have n cameras, each one of, or n sensors, each one of them is producing a stream of values, right? So A0 through AN-1 represent data coming from n sensors. And each sensor is producing k bits of data at a time, right? Every time it produces data, it produces k bits. What the multiplexer lets us do is, it lets us select. So S is a selector. And it helps us select one of the n, and then routes it So let's say AI. So if S represents I, then I'm going to connect AI to B. So kind of the idea is B is AI if S is selecting I. And S is one hot coded. So that can be the same as saying if the ith bit of S is 1. So the baseline multiplexer, the select bit is one hot coded. So if I have n sources, then I will have an n bit S, and exactly one of those n bits would be 1, and that tells us which source to select. So it's kind of analogous to if you have a TV, then which source should display on the screen. If you have a computer with multiple keyboards, then which keyboard should be allowed to talk to the CPU, right? Which keyboard's data is forwarded. So we often have in real world these situations where I have multiple sources, and then based upon something, I'm going to select one of those and forward the data, right? It's kind of like a router. It selects from n and routes to 1. That's what's happening. So it's kind of data selector or data router, or whatever you might want to call it. So it's referred to as multiplexer because it's essentially allowing us to take large number of information sources and multiplex them into a single output. That's what's going on out here. So we are going to pick this thing up on next Monday. But today we covered two very important building blocks, decoder and encoder. We saw you can certainly implement them using good old Karnaugh map approaches, but what we saw very importantly is that how we can take smaller decoders and make bigger decoders, or smaller encoders and make bigger encoders out of them. And that's kind of the main takeaway for today. And this multiplexer is something that we are going to cover more of that on Monday. So before I hang up, any questions? Okay, so if not, let's stop out here and hopefully see you guys, some of you in the office hours on Friday. Okay, bye.
Thank you, Professor.
Yeah, thanks. And again, apologies for the truncated lecture for today.